the Apple computers were the first step towards having computers everywhere. So Apple's mission in the beginning was essentially to make computing power available to as many people as they could. Also, interaction techniques of computers developed over time. So if you look back, the mechanical devices or the keyboard were fairly primitive and not useful to input graphics data, for example, to point at things. And so this was the first mouse developed at Xerox PARC that essentially led the way towards graphical user interfaces where you can point and click rather than input commands via a keyboard. So if you look at the technology, of course, the implementation of the mouse was fairly primitive, but essentially the idea behind it remains the same today. And so these are a little bit more recent artifacts. We have mobile devices like tablets, smartphones on the right. On the left, we have touch tables where you can do shared meetings, where you can interactively move around things, have multiple screens and video cameras at the same time. So these days, these communication technologies are ubiquitous. They are used by many people, millions of people throughout the day. There are billions of users of smartphones around the planet. So the question is, what more can we do? Well, it turns out that these new technologies also offer a whole set of new opportunities. These days, almost all homes are networked. All of you probably have a smartphone, if not more than one. So you can access your data anywhere you like. Your fridge might have an internet connection. Even your cat might have an IP address. So pretty much everything will be networked. If it's not now, then in a few years' time. And so that whenever some device or some user interacts, downloads a web page, puts a picture on Facebook or a comment on Twitter, essentially you produce data. And this is accumulated in several databases throughout the internet. Facebook, Twitter, Google, even UniSA have large databases that essentially record what you do on the internet. And so now the question, or one of the opportunities is, how can we make use of that data? How can we look at the data, aggregate it, extract common structures, behavioral profiles, see which users have expertise in what area, and perhaps leverage that knowledge to make better decisions and be more informed. Yeah, so among the challenges that we need to address is essentially how do we make sense of all the data? How do we interact with computing so that we don't need to be aware of that we are interacting with computers? So if you remember the mouse or the keyboard I've showed you, then the interaction and the interaction with the computer is pretty much one way. You sit in front and you input some commands and maybe you get a picture or a video back. But we will see in a few minutes that at the ASARC we do a lot of work in trying to hide the computing technology behind everyday artifacts. What if you could wear your computer instead of sitting in front of it? What if you could use natural gestures to interact with your machines rather than using mouse and keyboard? And so these are very exciting new technologies. A lot of opportunities there. Also, how do we process the data that we have collected? So these are not just megabytes or gigabytes. These are several orders of magnitude larger. The question there is, if you want to analyze and make sense of that data, no single computer will be powerful enough to do the job. So we need to distribute our algorithms, to distribute our data among a large number of computers so that we can collaboratively analyze the data, merge the results, and make sense of it. Yeah, so here at the ASARC, essentially we try to address these challenges in three major research groups. So the first group would be the Human Embedded Computing Group, which mainly looks at augmented reality and human-computer interaction techniques. So augmented reality basically means that we use IT technology to augment or modify the real-world environment. Human-computer interaction particularly deals with how do we interact with computers. And so I'll show you a video on the next few slides what work we do in that area. I myself are from the Semantic Systems Group. So we are mainly dealing with knowledge representation, automated reasoning, artificial intelligence, and software engineering. So we are looking at how can we capture and express the knowledge that underlies our business processes, our engineering design decisions, for example. How can we make the computer capture it, reason about it, and then present it in a meaningful way to the user at the time it is needed. We also look at how we can structure large software systems so that they remain scalable in order to process their data. And so the third major group is the Strategic Information Management and Data Analytics group. So there our researchers look at how we can manage data in enterprises, the underlying processes, the adoption of information technology for managing and distributing information, and also the collection and analysis of the data. So is the data of good quality? Is it consistent? Trying to identify patterns in large data sources. For example, looking for causal relationships between interactions of proteins in certain medication trials would be an application of data analytics in this context. So let's have a look at what the Human Embedded Computing group does first. So here you see one of our systems that was built perhaps about 10 years ago, if I'm quite right. And you see that yeah, it looks quite unusual. It consists of a belt with the batteries and a backpack. We have a helmet which has a camera, a see-through display, a GPS, and some other sensors on it. And so now you can actually take this system, put it on, and walk around. And so if you do that, this is what you'd see from inside of the system. So you have your gloves, which are used for interaction with the system. So rather than a mouse and a keyboard, you use pointing and the gestures with your glove. And so now by looking through the display, you can see the real world and overlaid with artificial objects. So here, for example, we have an artificial picnic table put on top of the basketball court next to the UniSA. And so you can pick it up, manipulate it, rotate it, and so basically augment your environment. And so other projects in this area are the following. So here, again, this is a similar technology with a see-through display where you try to simulate the burning sensation, essentially, on your own hands. And this has triggered some quite interesting emotional reactions by the users who've tried that before. But we can also use it not just for visual effects, but also for haptic effects. So here, for example, we have an augmented reality tool where you can use this pen, which is attached to this device, to paint on a virtual model. So we have this virtual model of a cat or a dog or whatever that is. And so now the user can see through the display and paint with colors on that virtual model, which is not really there. The interesting thing about this is that in addition to the visual perception that you also get the haptic perception, the force feedback from that pen as you touch the object. So it turns out that this is very important for the realistic effect that this immersive experience provides. But we can even hide computing technology more. So one of our students was recently involved in a project that was about interactive theater. So some of you might have read books that at the end of each chapter allow you to continue the story in a variety of ways by selecting a number of different options. And so this was a similar experience in a theater. So the users or the audience were given wireless devices which allowed them to make choices to influence the play at certain points in the act. And so in addition to that, augmented reality was also used to create the entire stage experience. If you look closely, you will see that apart from the actors, all the stage environments, the furniture, other characters, are all created by projection. So we used a large number of projectors to project essentially all the environment onto the stage from different directions. And so this is technologically challenging as well as quite interesting to watch how that the interaction between the technology and the actors unfolds. So, but of course, our research also has more practical applications. So rather than looking at theaters, we look at industrial design. So in industrial design, you have the problem that if you want to get feedback on your design prototype, you have to make an actual model, show it to your users or to your customers, and get feedback. If they give you good or bad feedback, you go back, modify the model, make an actual new artifact, and then show it again. So that, of course, has large lead time, and it is cumbersome and expensive to make all these models. So now researchers in our group thought, what if we actually get rid of that? We just use augmented reality, in particular computer projection, to get around the need for building a model. I'm sorry. So what you see here is essentially a real model, a real car. So this is made out of styrofoam or white plastic. And all the colors and the shapes are painted onto it virtually. So you have this virtual tool that you hold in the hand. And you can use it like a spray gun, essentially, to spray colors on this virtual model. And so that easily allows you to try out different creative decisions, different designs, until you arrive at one that pleases your aesthetics. Similarly, we can use that as part of the physical modeling process. So very often it's not enough to just have the physical artifact at hand. You also need a CAD model, a computer model, a 3D model that will later allow you to manufacture whatever you've designed at industrial scale. And so the step from the actual physical artifact to the model is usually non-trivial. Either you sit down manually with a CAD system and recreate the model as close as you can, or you take the model and scan it using some 3D laser scanner in order to make the model. But that is expensive and quite noisy. So our group investigates technologies that allow you to do both at the same time. They track your tools as you manipulate some styrofoam, for example, and as you do that, simultaneously create the 3D model. So the second step, the need to create the 3D computer model from the actual artifact, disappears. We also use augmented reality for training purposes. So here you see a project that Bruce and Intel did together. So in that context, we have here some kind of physical machine, a setup with different pipes, it seems. And so the task is to train your maintenance engineers to perform certain tasks on that machine. And so unfortunately, the configuration of this machine is quite complex. And so you need to do certain steps in a certain order, and at certain steps you need to make sure that the setup of the machine is in the correct position. Otherwise you might damage the machine or you might get injured. And so now AR can help you to train your engineers do that. So you can set up a training environment where you actually project onto the actual machine the instructions, as you see here on the top left, but also some color codes, for example, or some cues as to what action to perform and where to perform it. Yeah, so that basically leaves the examples from augmented reality. Just one last from computer graphics. So our computer graphics group also offers game design courses where you will learn how to design different genres of games, how to do the graphics that underlies the games, how to design the appearance and the character of your actors. And also, my part in that is to teach you how to do artificial intelligence to the degree that your computer opponents can play sensibly. Yeah, so now let's look at another group. Let's look at what we do in the semantic systems group. So we in particular are concerned with large-scale systems for knowledge representation and knowledge processing. So these days, the days where you have a computer in your basement and it does all the work for you, or you have got a computer in your study, are long gone. These days, industrial applications of computing are all on large-scale parallel machines. You have many hundred of machines together that run the same application, simulations, and so on. For example, if you look at Google, Facebook, Twitter, all of these run in massively parallel distributed applications. This is the only way to ensure that they scale appropriately. If millions of users are trying to hit the same application, the same page at a time, there is no single machine that can serve that demand. Instead, you need a distributed architecture which on demand adds and removes machines as they are needed. This is kind of pay-as-you-go model. Many companies have adopted that. They've outsourced part of their IT infrastructure into what we call the cloud, which is essentially a large number of computers running in data centers, are managed and administered by professionals. And so we can make use of that to simplify our IT infrastructure. For example, Google Docs. You don't need to worry how to write a word processing engine, how to install it, maintain it. All you need to do is sign up for an account and you can write your Word documents and edit them collaboratively. So that simplifies the IT infrastructure quite a lot. And so here we will look at how to engineer such systems. Unfortunately, there's quite a bit of complexity in there. If you look at this analogy, it doesn't take much to build a doghouse, right? Pretty much anyone can do it. There's not much engineering to do. You can just basically get started. If you don't get it quite right, it will still work more or less. Your dog might complain occasionally, but it will be okay. On the other hand, if you want to build the Sydney Opera House, then you have to plan carefully. You have to employ qualified engineers that really know their stuff. Otherwise, the whole thing will collapse. And it's the same in software engineering. In our networking and cloud computing degrees, you will learn how distributed applications are designed, how they are administered and wired together, and how they are monitored and run. So our programs have parts of software engineering, system design, networking, and systems administration and monitoring. So going back to our research activities, we also built and analyzed distributed systems that may run on the cloud. For example, we built low energy sensors for corrosion monitoring. So these have been devices like these in large numbers have been deployed on some bridges. And so they essentially monitor continuously the state of the corrosion of the metal in that bridge. And so they send that to, they collect that information and it's available in real time to the engineers to see how the bridge developed over time, how the state of the entire structure is at any moment in time. And so that is a vast advantage compared to what you had to do previously, where it required inspection, regular inspections of certain structural elements at certain times. We also built models of such systems. So, for example, if you've used internet telephony, voice over IP, then there are certain protocols like the Session Initiation Protocol or SIP. And so when you build and design protocols like that, you want to make sure that the protocols are correct, that there cannot be any problems with the protocol, that security is maintained at all times. And so by modeling them in a mathematically precise way and reasoning about protocols and their use and its use, we can prove that certain problems cannot appear in a given specification. Or if they appear, we can show how they can appear and perhaps find ideas how to eliminate the problems. We're also looking at finding faults in distributed systems. So although we can verify some properties, of course, as soon as you have a programmer that writes some code, programmers are human, we make mistakes. The specification that we work on may not be very precise or very good. And so in the end, something will go wrong sooner or later. The question is, how can we fix the problem? So we developed tools and artificial intelligence methods that analyze running programs, how they crashed, and give the programmer hints to how to more quickly fix the problems in our programs. Another large part of our work revolves around systems integration. So if you look at any normal enterprise, normally you would have a large variety of systems. They all come from different vendors in different departments. They hold different data, which to some degree overlaps, but it also has some unique features in each department. And so now the question becomes, how do we integrate all that data into a coherent global picture so that we can always at any point in time see what the state of our enterprise is at the moment. And so one way of doing that is simply to write manual programs, these little red boxes, that basically pull the data from one system and feed it to the next. However, that is a very tedious task. And in particular, if your applications keep changing, you upgrade versions, and so on, these red boxes tend to break. So our research group has developed methods that allow you to model both the data that is contained in each of the systems, as well as the format in which they are stored. And so then we can use these models to describe transformations, how to extract the data from one system, how to transform the extracted format into a format that our target system can understand, and then push the data from one system to the other. And so that allows us to build very flexible systems that can evolve over time as the IT infrastructure changes within your organization. Similarly, we're looking at processes. So processes in an organization hardly ever remain constant. They keep changing. Different projects, for example, may require different development practices, simply because all projects are slightly different. And so in most enterprises, what you have is a generic framework that governs how the enterprise works, but it needs to be adapted to the requirements of a particular project or a particular context. And so we have developed tools that take these generic processes and allow you to customize them to the particular needs of your projects. And so that was much more consistent and there were much fewer errors than the previous manual attempts to do the same at Siemens, for example. Yeah, what's the time, by the way? Okay. Yeah, given the time, I might skip over that. So we also try to capture knowledge from different sources. So, for example, in the health domain, we are concerned with extracting DNA data from breast cancer screening results and collate them in a common database that will then serve as a future reference for genome researchers. And so basically, together with some Australian projects, ANS and Nectar, which are sponsored by the ARC, we try to essentially make the data then available to all other researchers in Australia. And so that they can collaboratively try to solve problems that no one could have solved in isolation. Yeah, and the data analytics part, essentially the main idea here is if you have a massive amount of data, then there might be some patterns in there that might be useful to know about. And so here, for example, this is the structure of the internet, or it was some years ago. And so you see, yeah, it looks pretty, but it's not too much information that you can get out of that. It would be much more useful if we could infer from this structure common patterns. For example, that certain nodes communicate with certain other nodes. And so now this information, that this node is strongly linked to some of the others, is much more useful than having all the information available, which may not give us much insight. So the job of data analytics research is essentially to find efficient methods to extract these useful relationships out of a large set of example data. And last but not least, we also look at privacy. So in context of data mining and data analytics, we look at privacy so that from the information that is available from several sources, no privacy relevant data can be inferred. On the other hand, we are also working with law enforcement agencies and government organizations to look at what information is actually captured on devices like smartphones, Facebook and other platforms, and see how they can be used to solve crimes more effectively. Yeah, so at that point I'm probably out of time and I'd like to conclude. So if you found some of that interesting, if you're interested in some of these topics, please don't hesitate to join us. So we might have aged a little bit since these pictures were taken, but essentially we are still as enthusiastic as at that time about the research that goes on in our groups. So if you like more information, please visit our website. It has all the information about our programs, links to our research projects, and more videos about several topics. Thank you very much.